So last time we started with differential equations. The plan for today is to see few techniques or to recall few techniques to solve first order linear differential equations. Most of them you already know from analysis. Then we will see also the geometric picture or geometric meaning of solving a differential equation. And then we will study the numerical methods for solving differential equations, since mostly this course and also in practical, for practical purposes, differential equations are usually solved numerically with the aim of different solvers implemented in computer programs. So we will see few analytical techniques to solve differential equations, but mostly most of the differential equations cannot be solved analytically. This is only to give you some taste on how to solve these specific differential equations of first order. So let's see what we've done last time. So we started with differential equations. We defined what's an ordinary differential equation. So this is some function f, which depends on the independent variable t in this case, then the dependent variable x. This x so is a function of t. And then we also have derivatives of x with respect to the independent variable t in our equation. And there can be up to n derivatives of x present, and in which case we are talking about a differential equation of order n. So there is another way of writing a differential equation. So I only change the names of the variables, and instead of t, the independent variable becomes x. Instead of x, the dependent variable becomes y. And then we have derivatives of y with respect to x. Here are a few examples. We've already done the first one. So x derivative minus 3t squared is 0. So in this case, f of x, f of tx and x prime is this left-hand side. So f of tx x prime is x prime minus 3t squared. And the equation is that it is equal to 0. Here we can separate variables. We'll return to this technique in a few slides, but here we can separate variables. So we put x's on one side, t's on the other. So dx over dt is 3t squared. This x prime can be written in this differential notation as dx over dt. And differentials behave like numbers. So we can here multiply by dt to put dt on the right-hand side. And then we integrate both sides. So we integrate left side with respect to x and right-hand side with respect to t. And what we get is the solution, which is a cubic function. So x of t is t cubed plus some constant c. To determine this constant, we need another condition, which is called an initial condition. So x in some for some time t, for some value of t, is some real number. And from this condition, we can explicitly determine c. Here is another example. We don't know yet how to solve such an example. So this is a differential equation of second order. Y second derivative plus 2 times y first derivative is 3y. In next week, probably, we will be already able to solve such an equation, such a ordinary differential equation. But for now, let's only see what does it mean to check that some y is a solution of a differential equation. So we claim that y of x is equal to some constant c times e to the power of minus 3x solves this differential equation. What we have to check? We have to check that when we take the second derivative of y, this is here, and the first derivative of y, this is here, and plug those expressions in our differential equation, the equation is really satisfied. So we plug this y double prime in the equation, y prime in the equation, and also the y in the equation. And we see that left-hand side and right-hand side coincide. So this means that the candidate for y really solves our differential equation. And before we continue, let's only notice what's the difference between ordinary and partial differential equations. In this course, we won't study partial differential equations. They are also important in applications, but our time is limited, so we will not be able to look at techniques to solve partial differential equations. But partial differential equations, let us only mention what are PDEs. So the difference between ODEs and PDEs is that in PDEs we have more independent variables. So we have here x and y. They are both independent, so y doesn't depend on x and vice versa. And then we have some function u, which depends on both x and y. And now we can take derivative of u with respect to x and also with respect to y. And then also higher order derivatives. So we can take, so those derivatives are in fact partial derivatives. That's why those differential equations are called partial differential equations. But as I mentioned, we will only study ordinary differential equations in this course. Let's look at a few examples of differential equations in real life. So differential equations, with differential equations, we describe some change quantities which change with respect to some variable, usually with respect to time. And one example is this Newton's law of cooling. So T is a temperature of the body. And this T infinity, this is the temperature of the environment. And this is a constant. So this is constant, this doesn't change. And what does this, and K is also some constant. And what does this law tell us? So this law tells us that temperature, the rate of change of the temperature is proportional. So the rate of change of the temperature is proportional to the difference between the temperature of the body and the environmental temperature. So this means that, for example, if the temperature of the environment is higher than the temperature of the body, then the body will start to heat. And as the temperature of the body becomes closer and closer to the temperature of the environment, the rate of change of the temperature starts to decrease. So the difference in the rate of change of the temperature decreases with time. This is Newton's law of cooling. And you can see that this Newton's law of cooling, the differential equation, is a separable one. So we have dt over d small t is k times this difference. And we can put capital T's on one side and small t's on the other. And integrate both sides. You all know what are the integrals of both sides. So on the left side, we get logarithm of the absolute difference between T and this temperature of the environment. And on the right side, we get K times time plus some constant. And now absolute value of the difference between temperatures is equal to E to the power of K T plus the constant. But since this C is a constant, we can make another constant out of it. So E times E to the power of C is our new constant, C tilde times E to the power of KT. And now, whether we take the absolute value or we don't, in fact, we can now forget about the absolute value, because so we put, if you have plus, if you have T minus T infinity, if this is positive, then we can just forget about the absolute value. While if T minus T infinity is negative, then we should multiply this by -1. But in fact, this -1 can be absorbed in our constant. So in fact, since this C tilde is a constant, it absorbs the minus. So we can forget about the absolute value and only write that T minus T infinity is C tilde times E to the power of KT. And this is the solution of our differential equation. And now we need initial condition. So initial condition then determines this constant. So we need to know the temperature, for example, at some time point. For example, at the beginning, at time 0 is T0. And then, so T of 0 minus T infinity is C tilde times E to the power of K times 0. So this is 1. So this is C tilde. So C tilde is exactly time at temperature at time 0, which is T0 minus T infinity. So what we get is T is then T infinity plus T0 minus T infinity times E to the power of KT. Okay, this was one example. So the result was, the solution was exponential function. Then let's look at another one. For example, a radioactive decay. We have some radioactive isotope, and YT is the quantity of a radioactive isotope at time t. And the rate of change of the quantity is proportional to the again is proportional to the current quantity. And this proportionality constant is here written as minus k, but it could be written only also only as k, but here k is positive, and since we want to stick to the case that k is positive, then we write minus ky. And this k is exactly logarithm of 2 over half-life. And we will check that, that this half-life really has a meaning which is suggested by the name. So half-life is the time needed for the amount to decrease to half of its current amount. So this t over 1/2 is time needed for the quantity to quantity to decrease to half of its value. So current value. This is some amount which is specific for every isotope. So it's given in advance or measured and written in tables. And we will see from the solution of this differential equation that this is indeed half-life. We won't go again over the process of solving this differential equation. Again, it's a differential equation of separable type. So we can put all y's on one side and all t's on the other. And what we get is, the solution is, again, exponential function. It is c, some constant, times e to the power of minus kt. And let's see that the half-life really has a proper meaning. So what we have to check is, let's say that at time 0, so y0, we can compute from this solution that y0 is c times e to the power of minus k times 0. So it is c. And what we have to check now is that y of half-life is exactly c over 2. So at the beginning, at the current time, the quantity was c. And if the half-life really has the meaning suggested above, then y at half-life should be c over 2. And this is just a matter of short calculation. So here we have y of t of half-life. We plug in t in our solution. So this half-life is, so since k is logarithm of 2 over half-life, half-life is logarithm of 2 over k. Note that k is a constant. That's why also half-life is a constant and vice versa. So we plug in this logarithm of 2 over k in our solution. Those k's here cancel. And what remains is c times e to the power of minus logarithm of 2. Now this minus 1 jumps into the exponent. So we have logarithm of 2 to the power of minus 1, which is just the logarithm of 1/2. And now e and logarithm are inverse functions. So e to the power of logarithm is just the argument. So it's just 1/2. So e to the power of logarithm of x is x, since e and logarithm are inverse functions. So what remains is 1/2. And we really get c over 2. Okay, and another real-life example is a simple harmonic oscillator. So the motion of the simple harmonic oscillator can be described, can be modeled by a second order linear differential equation of this type. So this x is the displacement. This oscillator only moves in one direction, so we have only x axis. And the displacement, so x at time is the position at time t. The motion can be modeled. So the simple motion can be modeled by this differential equation. So this omega is some real number. If there are also other external forces present, we would have on the right-hand side also some force at time t. And we will study how to solve such an equation and what is the meaning of the solution for different situations, also in the presence of the force in a few weeks. So we'll know exactly how to analyze second order linear differential equation and what happens if we have a force and what happens if we don't have a force on the right hand side. Okay, these were a few examples. We will see even more examples in the process of studying the solving of differential equations, but this is only for the beginning. So let's only repeat what we've said a few times by now. What does it mean to solve a differential equation? So what we mean by solving a differential equation. So we have this ODE. So from now on, I will just say DE or ODE, and I will mean differential equation by this. So what does it mean to solve such DE? We have t as an independent variable and x as a dependent one. So to solve such DE, it means that we find x of t. This is some function from some interval where we are searching for the solution into real numbers. So we find a function x of t such that this equation is satisfied. So such that this function satisfies our initial DE. This is all what we have to determine. So to find a function x, which depends on t. So analytically, it's not very likely we will be able to solve x of t explicitly. Today we will learn some techniques how to solve such a DE analytically, but in most practical applications, the differential equations are too complicated to solve analytically. But we will study numerical methods which approximate the solutions. So numerical methods, the most basic one is Euler's method. This is very basic method, very easy to understand, but it's not very practical because we make a big error using Euler's method. However, generalizing this method, so generalization or improvement of this method gives us methods which are much more accurate and much better for practical purposes. And the method which is most well known, and we will also use it, is Runge-Kutta method. It is also implemented in MATLAB, and the function in which it's implemented is ODE45. And then you have arguments. We will see, so what's the idea behind Euler's method, and then the generalization, and we will also see why 4 and why 5 here. What is the meaning of this 4 and 5 in this function? Okay, but for today, for the first 2 hours, we will see few techniques to solve differential equations analytically, so that you get a taste for solving differential equations. And most of those techniques you've already seen last year in calculus, but even if you don't remember them, we will go over them in the next 2 hours. And we will also learn few new techniques. So if there is any question, just interrupt me. Okay, first order differential equations. So first order ODEs are ODEs where we only have the first derivative present. And if we only have first derivative present, then we can write, so first order ODE, it was f of tx x prime is equal to 0. But out of this equation, we can express x prime and put it on one side. And what remains is a function of t and x, and we put it on the other side. And this is then some function of t and x, and we write it as small f. So the general solution, so we know that solving such an equation is determinant x of t. And the general solution of such a ODE is a one-parametric family of solutions. So a general solution is a one-parametric family of solutions. This means why one-parametric? One-parametric because we expect 1 degree of freedom. So this one parameter C, since we have first derivative present, so the solution won't be completely determined, won't be unique, but it will depend on one parameter. It's the same as if we integrate both sides of this differential equation. You know that so the indefinite integral is unique up to the constant. So here, if we integrate both sides, we get a constant. That's why the solution is a one-parametric family. And you can also see, so if we had a second derivative here, then we would integrate twice and we would get 2 constants. So the solution would be a 2-parametric family. So in general, if we have an nth order differential equation, then we have, then the solution is an n-parametric family. For each indefinite integral you take, you get 1 additional constant. So geometrically, what does this mean geometrically? For example, the solutions are some curves. So you know from the chapter on curves that if so the solution is one parametric, this t is a parameter. So it's so if we fix c, then x of t and fixed c is some curve. For example, this is some curve, x of t and c fixed, let's say c 0. And then at some other c, This is another this is another curve. For example, this one. So this is at x of t c1, and for other c, it's another curve. For example, this one. This is for x of t c2, and so on. So the solutions are curves. If the d is nice, then they are smooth curves. And yeah, so they depend, the position, the specific, which of those solutions is the right one depends on this C. This is a general solution, general solution of a D. But if we would like to choose a specific solution out of those family of curves, then we need initial condition. So 1 point, so we need 1 point, one condition, 1 point on our curve, for example, this one. And so we have, if we have this one, then our solution is specifically this curve. So if we have, if we would have another, let's change the color. So if we have another condition, the blue one, for example, this one, then the solution would be this curve. So when we specify this initial condition, we specify a particular solution out of the family of solutions. But there might be also exceptional solutions, which are called singular solutions. So they are not part of the family of solutions, but they are singular. For example, there might be some line or some point or some other degenerate solution which doesn't come as a solution of this form. So those singular solutions are exceptional, and we have to look for the existence of such singular solutions when we are solving a DE. Okay, and now we will focus on special right-hand sides of such a DE. So this function f of tx can have a special form. And for those special forms, we will be able to solve such a DE analytically. And the first form is what the form we've seen a few times today and also last time. So when we can write this function f of tx as a product of two functions, one which depends only on t and the other which depends only on x. In this case, we are talking about a separable case. We can use separation of variables. So this is the first case. Our right-hand side, this f of tx, is exactly the product of two functions. The first depends only on t, and the other depends only on x. So we can separate variables. So we can write dx or gx equals to dt or ft dt. Ft times dt. And now we know what to do. We just integrate if the function g and f are such that we can compute the indefinite integral explicitly. So if g and f are transcendental functions for which we don't know how to integrate, then again, we are not able to solve this equation analytically. But if g and f are integrable, so meaning that the indefinite integral can be explicitly computed, then we can solve this equation explicitly. So yeah, the method is by integrating both sides. It's written here. And many times the solution of such an equation is exponential. We've seen two examples above. So when the rate of change of the dependent variable is proportional to the current value, then the solution of this differential equation is exponential function. So we have this form of the dE, and then separation of variables and integration gives us a solution which is exponential function. However, even if the right-hand side is not that easy, even if we have a second order polynomial on the right-hand side, which has simple real zeros, then we are able to integrate in this step. So if we replace here, instead of k times x, if we have here k times x minus alpha times x minus beta, where alpha and beta are real numbers, then we will still be able to integrate. If you remember from calculus how to integrate such a function, so here we will be integrating 1 over x minus alpha times x minus beta. And I will let you think for a minute, for a moment or two, how you would integrate such a function. So this is only a specific example, but the same method applies even if we had here x minus alpha and x minus beta. So here we have alpha is 0 and beta is 1 in this example. Beta is 1, yeah. And so we have kx times 1 minus x. We separate variables and we have to integrate this rational function 1 over x times 1 minus x. And what we do is use, so what we did here is partial fractions. So 1 over x times 1 minus x is some constant a over x plus some constant b over 1 minus x. Yeah, and we only need to determine the constants a and b. So what we do is here, we put everything to the same denominator, a times 1 minus x plus bx over x 1 minus x. And then now we can determine a and b explicitly. So we can only compare the numerators. And one easy way to determine a and b without long derivations is just plug in x is 1 once, and what we get is on the right hand side we get, on the left hand side we get 1 is equal to, so the first factor a times 1 minus 1 disappears, and what remains is b times 1, so b is 1. And now we plug in x is equal to 0. And on the left hand side, we still get 1, while on the right hand side, we get a times 1 minus 0, so A times 1, plus B times 0. So only A. So A and B are both equal to 1. Yeah, that means that here it should be plus. And we integrate both of those functions. Once we get logarithm of x, and once we get logarithm of 1 minus x. Let me check again. So A times 1 minus x and bx. Yeah, this should be correct. We get this. Yeah, so here it should be plus. Yeah, and so we know how to integrate both sides. And when we express x out of this equation, for the solution, we get a logistic function. X of t is 1 over 1 plus some exponential function. And this is called the logistic function. We've seen this model. So we've seen logistic function at the beginning of this course. The logistic model, if you recall, was such a model that the function first behaves exponential, so grows as exponential function, then the growth linearizes, and then the growth stops. So this is one specific example of a logistic function. Oh yeah, sorry. So here it should be plus. Yeah, here is okay, it's plus. But when we integrate, of course, we get here logarithm of 1 minus x. But since we are also integrating this denominator, we get this minus from the integration. So here it's really minus. So here it's really minus, but here it should be plus. So yeah, now it's correct. So only this minus was wrong. But there are also other examples. So on handouts, you will see another example, and you can work it out by yourself. So to conclude this first hour, let's see again where do those models we've just seen appear in real life. So the first one, the first model is exponential model. Whenever the quantity changes with proportional to the current value, we get as a solution this exponential model. We've seen a few examples before. So in biology, when also in chemistry, so radioactive decay, and so on. Then the logistic model. So this second example we've just seen is the logistic model. In the logistic model, the rate of change of the current quantity is not proportional only to the current size, but also to the capacity of the environment. So we have this factor x times 1 minus x. So when x is small, this 1 minus x is, so for x small, 1 minus x is approximately 1. which means that the growth is approximately k times x. So the growth is approximately exponential with what we know from exponential model. So exponential growth. But then x increases, and as x increases, 1 minus x decreases, and it goes to 0. And so this second factor has an impact on the rate of change. So the growth, the rate of change is decreasing. But in the limit, so in the limit when x goes to 1, this 1 minus x becomes 0. And the growth stops. So when the capacity of the environment, the maximum amount of the population is reached, the growth stops. And this is the meaning of this second factor, 1 minus x. So we would have here x max minus x, or if we just divide out by this number x max, we get 1 minus x over x max. And this x max can be put to the constant k. So that's why it's enough to study this x times 1 minus x model. So yeah, this logistic model takes into account, except the size of the population, also the resources which bound the maximal size of the population. But then we can have also more general models. So in general models, it depends on the problem, but the right-hand side can be kxt, so some function of the size and time times some function of the size. And there is also another way of using those two models, kx and x times 1 minus x, when studying information spreading. This is explained on the next slide. So another explanation is, so let's say that x of t, so this is information spreading. Let's say that x of t is the ratio of people from the given group, which at time t know some piece of information. And there are two ways of spreading. So the first way of spreading is spreading through an external source. So this spreading doesn't depend on the, is independent from the size of the population or size of the group which already possesses this information. It only depends on the number of uninformed people. So this means that the rate of change is proportional to the current uninformed ratio. So let's say that the uninformed ratio is 1 minus x, and the information spreads from external source only within this uninformed group, and the rate is proportional to the size of this uninformed group. However, the other situation is spreading through word of mouth, which means that the informed people tell the information to uninformed ones. So what's here important? Here it's important the product of the encounters of the informed and uninformed part of the group. So the rate of change of the informed ratio of people is proportional to the product of informed people and uninformed people. So the bigger this product, the quicker the spread of the information. And this is another way of using this logistic law. Okay, this is all for this first hour. Are there maybe some questions?
Yes, can you please repeat what's the difference between these two possible models?
Okay, if not, then we continue in 15 minutes.
Oh,
So
there was a
10,
question. There
20.
was a question.
So there is a question in the break about this spreading through an external source and spreading through word of mouth. So you can also, there is also another explanation how you can understand those two laws. So it goes for probabilities that each of the encounters of the information and the person is successful. So let's say that in the first case, we have this external source. And let's say in delta t, in time delta t, this information meets k people. So k people is met by the information. And for each specific person, what's the probability that it will get informed? So what is the probability that each specific person will get informed? So the probability is exactly the probability that the specific person will be from the uninformed group. So the informed group is X, so the ratio of informed people is X. That's why the ratio of uninformed group is 1 minus X. So the probability that each specific person will get informed is 1 minus X. So it's exactly the probability he or she will be from the uninformed group. So this is for the first law, and for the other, word of mouth. Again, delta at time delta t, our k, or let's say k tilde, it's not exactly k from the law, but let's say k tilde is some constant which tells us the number of meetings of two people. So two people in delta t, there are k tilde meetings of two persons. And now what's the probability that each of these meetings will increase the number of informed people? So what is the probability that each meeting will increase X? So one person must be from the informed ratio and the other must be from the uninformed ratio. So one person must be from informed group and the other must be from the uninformed group. So the person that one is from the informed group, so the probability that one person is from the informed group is X, and the probability that the other is from the uninformed group is 1 minus X. So then this probability is that one is from the informed and the other is from uninformed is X times 1 minus X. And it could be that, also the permutation works. So in fact, we have to compute, multiply this by a factor of 2 because it can be A is from informed and B from uninformed or vice versa. That's why I wrote here K tilde, because this K tilde is in fact, then K is in fact 2 times K tilde. So K is then 2 times K tilde because of possible permutation. But in any case, the word of mouth law is proportional to the product of X and 1 minus X. Okay. Before we continue with the techniques to solve these first order linear differential equations, let's jump a little bit and to see the geometric meaning of solving differential equations, so that you will have a better picture in head when thinking about solving differential equation. So geometric picture of DEs. So we have y prime is equal to f of xy. This means that in every specific point of our plane, we know the derivative, the first derivative of y. So if I draw here xy plane, let's say that we are in point x naught, y naught. So at x naught, y naught, let's say that in this point, we compute f of x naught, y naught, and this is equal to y prime at point x naught. So this is exactly the slope of the tangent to our curve at x naught. So we can, at x naught, the slope of our tangent is, let's say, this one. And then we come, so we move along this tangent for a small quantity, and we come into, let's say, x1, y1. And we compute again from this, from our DE, we compute the slope of the tangent in the point x1, y1. So f of x1, y1 gives us y prime x1. And the slope is, let's say, this. And we move along this tangent for a little bit. And we come in another point. And we continue the process in this way. So x2, y2, we can compute another slope. And so on. So if we take a grid which is enough dense, so enough x's and enough y's, and draw those arrows which represent the slopes of the tangents, then we can geometrically solve this equation without even writing the solution analytically. We just follow the tangents at each point. So we follow a tangent a little bit, and then another tangent a little bit, and another tangent a little bit, and so on. Of course, we will do numerical mistake because we cannot follow the tangent for an infinitesimal quantity, so we follow the tangent for some discrete quantity, which means that we do a little mistake, a little error at each step. But the denser the grid, the more accurate our solution. So that's what we are doing when we are solving a differential equation. We are just following the tangents at every point. And this can be visualized with MATLAB. I have a code here, so we'll see. So for example, this direction field. So we will draw direction field for the equation dy over dx is minus y. So in this case, we take for k, we take minus y, and the model will be exponential. So we have, okay, here it would be better to have x and y. So what we do is compute enough points on the interval between -3 and 3, and also y is on the interval between -3 and 3. So what I'm computing here is just computing those the grid of x0, y0, x1, y1, x2, y2, and so on the interval between -3 and 3. And then here I compute the values of the slopes of the tangents at each of the points of the grid. So it's by this, by our equation, it's minus y. So if we had here minus y plus 2, I would put here minus y plus 2, or minus, if we had minus 3y plus 1, I would put here minus 3y plus 1. And here I compute what's here, square root of 1 plus s squared. This is just the length of the vector. So we have, for example, this direction, the vector, the direction of the tangent. So this is, I put here to the difference in x's, the difference in x is 1, and the difference in y is exactly the slope. Because if I take for delta x, if I take 1, then delta y is slope of the tangent. So it's just y prime at the point x. This is xy. So this point is xy. So the slope is then y prime x. So if I take the difference in x-axis to be 1, then the difference in y will be y prime x. So the length of this vector, this is v, then the length of this vector is square root of the length of x, the change in x squared plus the change in y squared. So it's square root of 1 plus y prime x squared. So this is what I compute here. These are those lengths of the vectors. And this quiver, this function is designed exactly to draw direction fields. So the first component are x's, the second components are y's, and then the third and the fourth components are vectors, the slopes, the slopes. So these are the first components of the slopes, slope vectors, and the second components of the slope vectors. And why I divide by L? So I divide by L to make all those vectors of unit length. So here I computed the length of each of those vectors, and now I just make each of those vectors of length 1. That's why I divide by L. So this vector, I just make V a unit vector. So it's 1 over, so this is L in the code. And then the second component is y prime x over L. Okay, and this factor only tells me for what amount should all the vectors be. So with what factor should all the vectors, direction vectors, be multiplied? So if we don't specify this, the image can be very dense and unreadable. So we can try to draw this picture without specifying this last parameter, but it could be too dense, so we should multiply all the direction vectors with some constant. And I tried and saw that in this specific case, it's good to multiply those vectors by a factor 0.45 to make it readable. So let's run this example. Okay, so this is figure 1. You see, these are directions. So if I start, for example, here at this point, then I will just try to follow the directions, and the curve which I will get is exponential function with, so exponential functions e to the power of minus something. And if I start some other point, again, I just follow those this direction field and get another exponential function from the family of solutions. You see this one, if the solution is constantly equal to 0, this is the singular solution. So if I start on the x-axis, then all the tangents will be horizontal, and then I remain on the horizontal axis. But if I start below the horizontal axis, so then I will grow, and asymptotically I will be nearer and nearer to the horizontal axis, to the x-axis. And the same can be done for another direction field. So here I choose differential equation y prime equals to 2y. So the solution is, again, exponential function, but this time the coefficient is positive, which means that the solution should be e to the power of 2y. And exactly this happens. So the solutions following this direction field, the solutions are usual exponential functions. And the third case is logistic model. So you see in the logistic model, for example, if I take y times 1 minus y, the logistic model, yeah. If I start, for example, here, near 0, I start growing. And then I'm, so exponentially, but then I'm just, the direction field become horizontal. And again, if I start from here, for example, from point 3, then first I'm falling exponentially, but when I'm reaching y equals to 1, then the picture becomes so horizontal. So those are the solutions of the differential equation. So geometrically, those lines, those curves. And you can try your own cases. So the code is the same for all the cases. Okay, this was geometric, meaning it's called the phase plane of our differential equation. And now let's move back to analytic solutions of differential equations. So we will also see linear differential equations. We've seen those linear differential equations already in calculus, but let's repeat the technique. So first order linear differential equations are differential equations of this form. Again, first order because only the first derivative with respect to t occurs. So this refers to only the occurrence of the first order derivative, while linear depends on the exponent of x. So x only occurs to the power of 1. If we had x squared in this equation, then this would be nonlinear differential equation, and we would not be able to solve it analytically. But first order linear differential equations can be solved analytically. And if you recall, the solving linear DEs consists of 2 steps. So we have this first order DE. First step is to solve the homogeneous part. This is, we put the right-hand side to 0. We have x prime plus ft of x is equal to 0. So we put this g to 0, and this is called the homogeneous DE. And we get a solution, let's say x homogeneous of t. We get one solution. So by separation of variables, for example, so by separation of variables, we get one solution. I mean, in fact, we get a family of solutions, C times X homogeneous of T. So this C is a constant. And then in the second step, we have to find one solution for the initial DE. So we try to find one specific solution of the initial DE. I will write this initial DE by star. And we denote this solution by xp of t. It's called particular solution. And how to find one specific solution? There are two ways. One is just by guessing. So guess. So we can just guess one solution. For example, we think maybe the solution is a constant. We try to plug in a constant, compute, and we get that the constant is really a solution. This is our particular solution. Or we can think that the solution is a linear function. We plug in a times t plus b, compute a and b, and really get a particular solution, for example. if our guess was correct. So it's some kind of wise guessing, and it might lead us to one particular solution. And we did this second step. If we are not able to guess the solution, there is a method called variation of constants. It requires some calculations, but it always leads us to solution. It might be that we will be computing a lot, and at the end, we will get a constant for this particular solution. That's why it's always good to try to guess the solution, at least to think of what form would be our solution. Otherwise, we could compute a lot, and then get just that the particular solution is, for example, 3. Okay, and once we have first step and second step, then in the third step, all solutions to the initial DE are of the form x of t is a homogeneous solution plus a particular one. So every solution is of this form. It is C times some. So let's here say that we have here particular homogeneous solution. So it's C times homogeneous solution plus particular solution. So all the solutions are of this form. And this C is a constant. And to determine C, we only need one additional condition. As before, for example, when we were solving the homogeneous equations with separation of variables. Here, we first have to compute the solution of the homogeneous part and do not plug any initial condition yet. First, we have to also determine the particular solution. And once we have both, we sum them up and then plug in the initial condition. Okay, and now I will just try to persuade you that this algorithm really works, so that all the solutions are really of this form. So first, we have here this homogeneous part. So we have here this homogeneous equation. And first, what we claim is that we find the particular solution, this x with index h of t. So let this be a particular solution of this homogeneous part. And then all the solutions will be C times this particular solution. Why is this true? So first, we have to check two things. So first, we have to check that first thing is that CXH is really a solution. To our homogeneous part. You already know that everything what we have to do is just plug this C times XH into homogeneous equation. And this is done here in these 4 lines. So we plug in CXH prime plus F CXH. do some calculations. And you see here, C, this constant C can be factored out. And in the parentheses, we get AXH prime plus FXH. And since this XH was a particular solution of this homogeneous part, this parenthesis will be 0. So C times 0 will be 0. So this proves, these 4 lines prove that every solution is of this form, of the form 11. So this was only the one, so one direction. So if we have one particular solution, then multiplying it with a constant also gives us a solution. However, the second step is to show that every other solution is of this form. And there is a trick to do this. So what we have to do, let us say that X index H is a particular solution of the homogeneous part. So X prime plus F T X is equal to 0. And let's say that X of T is another solution. Of this same equation. And what we would like to prove is that X over XH, so if we divide the function X with the function XH, we get a constant for every T. So we would like to prove that we get a constant C, so the same constant for every T. So this is what we would like to prove. So in other words, this is equivalent to saying that if we take derivative of both sides, that so on the left-hand side, we take the derivative of this quotient, while on the other side, we get the derivative of C, which is 0. So this is what we want to prove. We want to prove that X over XH prime is equal to 0. And let's compute this prime. So X over XH prime. This is by the rule for taking derivatives of the quotient. It is X prime times XH minus X times XH prime over XH squared. So this is what we know from calculus. And now I can use that X prime is equal to, so here I will use that X prime is equal to, so that X is a solution of our differential equation, which means that X prime is equal to minus Ft times X. And the same for XH prime. So XH prime is equal to minus Ft XH. And I just plug these two expressions into our quotient, and we will see that everything cancels out. So we get minus Ft XH, and then minus X, and then minus Ft XH over XH squared. And we notice that in the numerator, the summands cancel. So we really get 0 because they are the same. So this proves that all solutions of the homogeneous part are really of the form some constant times a particular solution. And by the same method, we can show that all the solutions of our initial equations are of this form. So you can try this by the same method. So we did, we did prove that all the solutions of the homogeneous parts are of this form. And by the same method, we can prove also that all the solutions of this initial differential equation are of the form CXH plus particular solution. Again, you do the assumption that we have one particular solution and then another particular solution. And what we have to prove is that the difference between those two solutions is C times XH. And for this, we use the same technique. And it's done on the next slide, so you can look at this by yourself. So you see, this is the second step. So first we have to check. So we have to prove two steps. First, in the first step, what's done here in this step. So in this step, it's proved that every function of this form, C times XH plus HP, is a solution of the differential equation. So it's a short calculation, 4 lines. And then in the second step, we take xt to be a solution of our differential equation. We take some particular solution. And what we prove is that their difference is in fact of the form C times XH. Which means, and this will prove that all the solutions are exactly some constant times a particular solution of the homogeneous part plus a particular solution of the non-homogeneous part. Okay, and for the end, let's look at for the end of the second hour, let's look at the techniques, a technique of variation of constant, which can be used to find the particular solution. I will explain on an example, but it works the same in general. There will be also a derivation in general on slides. So let's say that XH of T is a solution of a homogeneous part. And what I do now, so all the solutions are then C times XHT, where C is a constant. C times XH are all solutions, of a homogeneous part. And variation of constants refers to this constant C. Now we change it to a function of T. So we change this constant to a function of T. And then what we claim that the particular solution is of the form C of T times XH of T. So the form of a particular solution. And all what remains to be done is to determine this C. And let's look at an example. So we start with the differential equation t squared times x prime plus tx equals to 1. And we will also have an initial condition x at time 1 is equal to 2. So what is the homogeneous part of this equation? So the homogeneous part of this equation, first step, the homogeneous part is t squared x prime plus tx is equal to 0. And we won't do a long derivation, but you can do it by yourself by a separation of variables. The solution is x, the solution of this homogeneous part is c over t, where c is a constant. So this is the first step. And now we do a derivation of a variation of constants. So we put x p of t is a function of, so c is a function of t over t. And we plug this into our differential equation. So we plug this into our initial differential equation. So what we get is t squared times, and then we have derivative with respect to t of ct over t plus t sine times ct over t is equal to 1. And let's solve on c. So we have t squared times, and now we take, I will use the product rule. So I will use ct times 1 over t. I will write this function as ct over 1 times 1 over t. And what I get is t squared, and then I first take the derivative of c times 1 over t, and then plus ct times the derivative of 1 over t, which is minus 1 over t squared. So I used product rule. Product rule. And then plus, and here t and t in the second summand, t and t cancel, and ct remains. I get 1. And then I just multiply the parentheses with t squared, and I get from the first summand, I get t times c prime of t. And then from the second, I get minus c of t and plus c of t equals to 1. And now this c and c cancel. And if you recall from calculus, from differential equations, this is not a coincidence. Using the variation of constants, always the second and the third summand will cancel out. For all linear differential equations, only the first summand, so the summand where we have derivative of the constant of c, only this summand remains in the equation, and so c prime of t is equal to 1 over t. So c of t, by integrating both sides, we get that c of t is minus 1 over, so it's logarithm of 2 of t. And in fact, I don't really need the constant because I'm only searching for a particular solution. I need only one particular solution. So here I don't need a constant. The constant not needed. I can always take this constant to be 0. So this is my particular solution. So particular solution is then, so c of t, recall from above, is C of t over t. So this particular solution is logarithm of absolute value of t over t. And finally, step 3, the solution of the initial differential equation is a sum of the C times homogeneous solution. So this is C over t plus our particular solution. So it's C times 1 over t plus our particular solution logarithm of absolute value of t over t. And now fourth step, our initial condition was that at time 1, the value of x should be 2. So we have x of 1 is equal to c times 1 over t plus, and here we have logarithm of 1 is 0, so plus 0 is 2, which means that for t I should here plug in 1. So this means that c is equal to 2. So x of t is equal to 2 over t plus, and now it remains to determine whether we take absolute value of t or t. So if we are on the negative side of the x-axis of t-axis, now t runs, so t is a parameter. So if you study t's which are negative, then we will take logarithm of minus t. But if we are studying t's which are positive, we will take logarithm of t. But since here we took for t, we took 1, this means that we are interested in t's which are positive. That's why we will study only t's which are positive. So we can take here logarithm of 2 of t over t without absolute value. Okay, is there any question regarding this derivation?
Yes, what was our homogeneous part?
It was this one.
Yes, so because down you wrote only c times 1 over t. So should it be c squared over t, or is it okay if you just use c over t?
C or t, so c is a constant.
Yes, no, below when you wrote the result.
This step 3 or step
yes.
Step 3. So it's c or t. Yeah, in fact, yeah, I should take here. So one particular solution I could take here. I should take here 1, in fact. And all the solutions are then c times xh of t. It's c over t.
Okay. Okay. Thank you.
Thank you for the comment. Yeah. So if I'm only searching for one solution, then it should be 1 over t, but all the solutions are then c times h, xh. So we've seen at the end of the last hour one specific example of a linear differential equation of first order. We solved it by the method of variation of constants. And now I will only comment on the general, so on the same method working for all linear differential equations of first order. So what we've noticed is that, so our particular solution was of the form c, which is a function of t over t. Then we plugged it into our initial differential equations, used product rule to differentiate this form. And what we've noticed is that from this product rule, only the summand consisting of the derivative with respect to c, of c with respect to t remains, and the other summand cancels out. So so cancels out with the linear part of the differential equation. So this was the linear part. This was f of t times x. And the second summand in the derivative of the particular solution was exactly, exactly canceled with this linear part. And we will see that this is indeed always true. So this is on slide 20. So here our x is y and our t is x. I only changed the notation. So we have this different first order linear differential equation. X is independent and y is dependent variable. So the homogeneous part is by forgetting about this g of x. We get y prime is equal to f of x yx. We do a separation of variables, and a general solution of this is then a function of this form, c times, and then e to the power, to the exponent, which is integral of f of x dx. So of course, for this method to work, we should be able to compute, we should be able to determine the indefinite integral of f. So f, integral of f must be possible to compute. And then in the variation of constant part, the c will become a function of x, and the general in the form of the particular solution will be this. So c of x times e to the power of integral of f of x. And now we will take derivative of this y, again using the product rule. Before this part was recalled that in the previous example we had c of t times 1 over t. So when we take the derivative with respect to x, we get c prime times this function plus c times the derivative of this function, and the derivative of this function. So here, to compute the derivative of this function, so we had e to the power of integral f of x dx, and we took the derivative. So the derivative of e is e, and the derivative of this integral by the fundamental theorem of calculus is just f of x. So we use fundamental theorem of calculus to compute the derivative of integral of f. In fact, we didn't even need it because here this integral was not definite, but it was indefinite. So what we in fact did is we took, so I will put this in the parentheses. So we would need fundamental theorem of calculus if our integral in the exponent would be definite, but our integral was indefinite. So what we did was only anti-derivation. So only the inverse operation of taking indefinite integral. So that's why I put fundamental theorem of calculus in the parentheses. It was too much to use it. So, okay, in any case, we get f of x. And now we plug this derivative into the initial equation. So we get, what we get is this line here. And as you can notice, the second term of the derivative is the same as the linear part of our differential equation. So the linear part, this means f of x times yx. And so they just cancel out. And what remains is this derivative, which consists of the derivative of c and the non-linear part, I mean the non-homogeneous part of our dE. So here, what we will get is that c prime of x is g of x over e to the power of integral of f of x dx. So it only remains, okay, this can be written as gx times e to the power of minus integral of f of x dx. So our c of x is then integral of this. So integral of g of x times e to the power of minus integral of f of the x dx. So this is then c. And you can see this in various textbooks in analysis, that the solution of the linear differential equation of first order is y of x is equal to, and then we have e to the power of integral of f of x dx, and then in the parentheses c plus this part, so integral of g of x times e to the power of minus integral f of x dx, and everything integrated. So this part is integrated with respect to x. So you might recall this equation from last year. Maybe you were using this equation in lab sessions. But in any case, you don't need to, you will also see it in textbooks, but in any case, you don't need to recall it. It's better to know the technique and then use the technique on specific examples. But yeah, you can just look at your differential equation, read out f and g, and plug them into this expression. And then calculate 1, 2, 3 indefinite integrals, and you are done. Okay, to motivate another technique for solving linear differential equations, let's define a problem. So problem, for example, we have a family of curves. And we would like to determine a family. We would like to find curves which are perpendicular to, in each point, to some curve in the initial family. So we would like to find curves which are in every point perpendicular to some curve in the initial family. And let's do a specific example to make this more clear. Let's say that our initial family will be a family of circles which all pass the origin and have a center on the x-axis. So once I've said that they have a center on the x-axis and that they pass through the origin, I've already determined explicitly this family. For example, if I take this to be the center and that the circle must go through the origin, then this is one circle in the family. And then I specify another center, then this is another example. And for example, this one will be this one, and so on. And I can do this in the on the other side of the y-axis. So we have circles which all have centers on the x-axis and go past through the origin. Okay, those curves don't look as a circle anymore on my picture. So the equations of those circles are determined. So let's look at one. One of them, the radius is c, and it goes through the origin. So this means that the center is c0, and the radius is c, which means that the specific circle has equation x minus c squared plus y squared is equal to c squared. So this means that on the left-hand side, we have a distance from the point, distance of the point xy from the point c0, and this distance squared of the point xy from the point as c0, and this distance squared must be c squared. So this must be c squared. And c varies. So our family is obtained when we vary c over all real numbers. Now this equation can be also rewritten. So we compute this first square and we get x squared minus 2cx plus c squared plus y squared is equal to c squared, which means that the c squared on the left and on the right side cancel out. So we get x squared minus 2cx plus y squared is equal to 0. So this is our family. And now we're searching for curves which are perpendicular. So let's say that we are in this point. So in this point, the tangent to the curve from our family is this one. But the curve we are searching must have tangent which is perpendicular to that one. So it must be like that in this point. And then in another point here, for example, again, the tangent must be like the tangent to the initial curve from the family is this. And since our family of curves must be perpendicular to the initial family, the tangent to our solution must be like that. So from the picture, I've drawn, it's not clear what we get for the, so I could, like before for directional field, those two green slopes, in fact, are two vectors in the direction field. I could do this for every point in the blue family, draw those green direction fields, and then out of those direction fields, I could see geometrically what is the solution to my problem. But in fact, it's possible to solve this problem explicitly, analytically. So what we know for those slopes is that they are inversely proportional. So they are different in size and inversely proportional. So if two tangents intersect, so if two lines intersect at right angle, then if K is the slope of the first, you know from analysis that the slope of the second must be minus 1 over K. This is what you already know from analysis. Probably you've used this fact already in high school. So for our blue family, we know that K for our blue family is y prime. So we have y of x is the equation of our curves in the initial family, and you know from calculus that the slope of the tangent is y prime. That's why y prime for our for the family we search is minus 1. So I will write here, let's say y tilde prime for the family we search is minus 1 over y prime. So if y prime is a solution, is a expression for our solution, then y tilde prime is minus 1 over y prime. So all what we have to determine is to find y prime. And if we find y prime, we'll have an equation. So if we know that y prime is some function of x and y, then we will know that what we will know is that we are in fact solving the differential equation minus 1 over y prime is equal to the same function of x and y. This is what we will have to determine. And if we solve this differential equation, we get a perpendicular family of curves. So what we have to do is to write this y prime as a function of x and y. But our family is given here. So from this family, we should somehow get rid of C, and there should appear the derivative of y with respect to x. And the simple idea how we would do this is just to take the derivative of this solution. So we take the derivative of x squared minus 2cx plus y squared equals to 0 with respect to x. And of course, we have to, here we have to take derivative implicitly. So this y, we have to know that y is not a constant, but it is a function of x. We take the derivative. I will write here in the parentheses implicit derivative, implicit, using that y is a function of x. So let's take this derivative. What we get is 2 times x minus 2 times c plus 2 times y prime is equal to 0. Here I took derivative with respect to x. Here I can cancel out 2's and I get c is equal to x plus y prime. So I expressed c in terms of x, y, and y prime. And if I plug in this c in the initial equation for the family, I will get rid of c, and I will be able to express y prime in the form y prime is equal to f of x, y. So now I plug in this c into our family. So I get x squared minus 2 times x plus y prime times x plus y squared is equal to 0. And from here, I only express y prime. So x squared minus 2x squared minus 2xy prime plus 2 plus y squared equals to 0. And then y prime is equal to minus x squared plus y squared over 2xy. So this is the differential equation. So the solution of this differential equation is a family of circles with centers on the x-axis passing through the origin. We know this by construction of this differential equation, that the solution of this differential equation is exactly the initial family. And as we said, to get the family of perpendicular curves, what we have to do is to exchange the left-hand side with minus 1 over y prime and leave the right-hand side as it is. So to get differential equation of the perpendicular family, perpendicular, I put perpendicular in the parentheses because I mean the family of curves which are perpendicular to at every point to some curve from the initial family. What we get, so minus 1 over y prime is equal to the right-hand side. Or in other words, y prime is equal to 2xy over x squared minus y squared. Okay, let me check if I did this correct. So y prime is so we started with the family of circles with radius a going through the origin. We differentiate with respect to x. We expressed y prime, and what we got was here. Did I do this correct? So a is 2x is minus 2c minus 2y y prime equals to 0. And then I express c, and I got 2y y prime okay, I think it's correct. So we get this equation y prime is equal to 2xy or x squared minus y squared. And now, how would we solve this equation? So it's not a linear differential equation. Yeah, I see. I see why I didn't get the same thing as in my notes. So I changed the symmetry. So in fact, I should start with the family of curves with centers on the y-axis. But I started with the family of curves with circles with centers on the x-axis. And yeah, that's why I got different than in my notes. So if I start with the family of circles on the x-axis, I get this. I get this expression. I get this differential equation, which I don't know how to solve. So we don't know how to solve this differential equation because it's not linear. Because it's not linear and first order. Let me check to try one trick. If it doesn't work, then I will change the symmetry of the problem, because in the other way we will be able to solve it. So I will try to transform this right hand side in the solvable form. So we get y prime is 2xy over x squared minus y squared. So in what we get in the numerator, so it's x minus y, x plus y squared minus x squared minus y squared. And then in the denominator, we get x squared minus y squared. So we get x, so we get x plus y squared minus x squared plus y squared over x minus y times x plus y. Okay, and we continue. So from the first part, we get 1 x plus y over x minus y. And from the second part, we get minus x squared plus y squared over x squared minus y squared. So this is, so if we continue, we get x minus y plus 2y over x minus y minus, and here we get x squared plus 2 plus minus y squared plus 2y squared over x squared minus y squared. And I think we won't get anywhere in the solvable form. So let's stop here. This won't work. So, okay, we derived the family, we derived the differential equation which we would need to solve to determine the family of perpendicular curves, but it doesn't seem doable. If we change a problem so that initial curves are circles with centers on y-axis and passing through the origin, our DE would be exactly opposite one. So we would get y prime is x squared minus y squared over 2xy. So our DE would be y prime is x squared minus y squared over 2xy with minus here. And this is what I wanted to get at the end. Still, this equation doesn't look first order linear differential equation, but we will see that it is homogeneous one, so-called homogeneous differential equation. So this is minus and x over 2y, and then plus y over 2x. And whenever you have differential equation which has y over x as a variable, so here we can introduce a new variable u is equal to y over x. We will see that our differential equation can indeed be solved. So we introduce new variable u is y over x, which means that y is u times x. And now we take derivatives, which means that y prime is, now u is a function of x. So here recall, here note that u is a function of x. That's why I have to take derivative with respect, also with respect to derivative of u with respect to x. So I get u prime x plus u times derivative of x is 1. And on the right hand side, I get minus 1 over 2 u plus u over 2. So this is with this substitution, this is 1 over 2u, and this is u over 2. And you notice what's this? Here I can here what I can do is, in fact, I can separate variables. So I can separate u's from x's. We in fact got a separable differential equation in u. So u prime x is minus 1 over 2u minus u over 2. And if I continue, I get minus and 1 plus u squared over 2u. So I put everything on the common denominator. And I can separate variables. So du over dx times minus 2u over 1 plus u squared is equal to dx over x. So I separated variables. And now I can integrate both sides. And yeah, here you have to notice that how to integrate this part is again introducing new variable. So v is 1 plus u squared, and then dv will be exactly 2u du. So what I will get here will be integral of minus dv over v is equal to integral of dx over x. And yeah, so you can continue because we ran out of time. So now you can continue to solve this equation, and what you will get is so 1 plus u squared is equal to c over x. And now we plug u is y over x. So 1 plus u over x squared is equal to c over x. And at the end, you get x squared plus y squared is equal to cx. So x minus c squared plus y squared is equal to 0 when c runs over real numbers. So, and let me only comment on this solution. So our initial family of the corrected problem was a family of circles with going through the origin with centers on the y-axis, and the family of curves which are perpendicular to this family of circles. The solution are exactly circles with the centers on the x-axis going through the origin. So, the idea was to demonstrate this homogeneous differential equation. So whenever you have expression, whenever you have a differential equation which is of the form y prime is equal, and then on the right hand side a function which can be expressed as u y over x, then you can introduce new variable u, and when you introduce this new variable u, the function, the differential equation becomes a separable linear differential equation, and you can solve it explicitly. So, and again, to return to initial data of our problem. So if you start with these green circles, the solution should be in fact those orange circles, because the problem is symmetric. So now you can think by yourself at home how we would solve, how we would show that this differential equation has a solution exactly family of circles with centers on y-axis. So the solution to this differential equation, which we didn't know how to solve, should be exactly the family of circles with centers on y-axis passing through the origin. And we will comment next time how to do this if it's even doable.